Today, we'll talk a little bit about GPU. We'll start with quite a high-level introduction to what GPU and GPU computing is, and then we'll do a little bit more hands-on with Stig Rune. Will show us a little bit how we can compile stuff for our GPUs, how we can find the right modules to use with GPUs, and also some container and GPUs and how that works. We have a short schedule here. We've changed the format a little bit for these days. We announced that a few days ago on the web page, but we'll do 45-minute sessions with 15 minutes break each. And I think for the two first session, I would like to ask people that we do audible questions during the break, but feel free to ask all the questions that you want on the HackMD. So we have all of the GPU team from NRIS is in the meeting and will be able to answer all of your questions regarding GPU if I miss something. So let's start by doing a quick introduction to GPUs. So we'll start talking a little bit about what a GPU actually is, because maybe some of you don't know what a GPU is and why it's interesting in a scientific context. We'll dive a little bit into the nitty-gritty details, again, from quite a high level. So we won't go into all of the programming details, for instance, of a GPU, but we'll see why a GPU is different from a CPU, for instance. Then we'll jump over to talk a little bit about the different software technologies that you might encounter when programming for a GPU. We'll look a little bit about what the vendors are doing. So what are NVIDIA and AMD sort of sponsoring, and what are the alternatives to using what the vendors are providing. Lastly, we'll talk a little bit about application areas for GPU compute. So what sort of applications would you transition to a GPU and expect some speed up? And when should you not go to a GPU? Because that's also an important topic when discussing GPUs. GPUs are not the one-size-fits-all solution to all of our problems, unfortunately. Yes, so let's get started with what a GPU is. And on this slide here, you can see an example of a GPU. It's the NVIDIA A100 cards. It's the GPUs that we have just got installed in Betsy. And it's actually quite a bit bigger than what you get the impression of here, but we'll come back to size a little bit later. So I've used the expression GPU quite a lot until now, but what does that actually mean? Well, GPU actually stands for Graphics Processing Unit, and it's one of the oldest accelerators that we have in our computers. And what I mean with accelerator is that it's an additional computing unit that is attached to our motherboard and is able to talk to the CPU and perform computations. So all computers need a central processing unit, the CPU, but then to do other stuff, we have accelerators to do a couple of things. And the GPU is one of the most common ones to find. Nearly all our devices have GPUs because nearly all our devices are connected to a computer. So in your mobile phone, there is a separate area on the chipset where the GPU is located, and I'll show you that in a couple of slides. Our laptops have GPUs. They can have GPUs integrated in the CPU, or they can have dedicated GPUs. Our workstation has them, and as I just mentioned, even our HPC servers have GPUs now. However, we will not focus on the graphics side of things today, but we'll focus on GPU, so general purpose computing on graphics processor units. Because in the beginning, when we got GPUs, they were set up only to do graphic computation, so doing stuff with triangles, calculating texture data, stuff like that. But then people noticed that these units are so powerful and are capable of doing other things. So actually, people started to hack GPUs to use them for scientific compute. And then the vendors decided, well, this could be a good area for us to actually go into. So we ended up with general purpose computing on GPUs. So usually in a scientific context, we see graphs like these. We see a tremendous performance gain by going to GPUs compared to a CPU. And I just wanted to dive a little bit into this because this is a truth with some caveats. Here we're looking at a graph from NVIDIA. They're talking about their BERT deep learning natural language processing models. And as you can see, one CPU is modeled as 1x on this graph, and the most performant NVIDIA GPUs are 250 times more, are 250 times quicker than a CPU. And this sounds excellent. Why don't we all just move to GPUs right away? Well, the reason for this is, of course, because this model is very much tuned to GPUs, but as we'll see, there isn't actually any magic. What we're seeing here is actually the latest Xbox system on a chip. And what we can actually see here is all of the computing in one chip. So the newest gaming stations like PlayStation 5 and the Xbox Series X don't actually have a dedicated GPU. They have just one chip where everything is fixed. And that's what we're looking at here. So you can see memory is on each of the sides, noted with GDDR6. You can see in the middle, it's the GPU. And I've decided to highlight the CPUs here with red because it can be a bit difficult to see. But in these two red squares, we actually have 8 CPU cores. And as you can see, they're dwarfed by the GPU. The GPU takes up a massive amount of silicon compared to the CPUs. And that's some of the reason why we're getting so much performance out of GPUs and why NVIDIA can brag about 250 times better performance on GPUs. It's, as I said, it's not magic. It's just that we're dedicating a lot of silicon to this. And we can go one further, actually. If we take the GPU nodes on Betsy, we can see that the size of the computing die is actually massive for the GPU. It's 11 times larger than our CPU. And with that in mind, it's almost a wonder that we are just using CPUs and not GPUs. And even more incredible that the CPUs can, in many tasks, be quicker than our GPUs. And we'll dive a little bit into why that is. So what is actually a GPU when we open it up? Well, a GPU consists of a ton of cores. We've heard previously in this workshop that we have around 128 cores on Betsy, CPU cores. But a GPU has normally more than 1,000 cores, and one single NVIDIA A100 has almost 7,000 cores, so 7,000 small compute units. And on Betsy, we actually have 4 of these cards connected to the CPU. So it's a tremendous amount of small cores compared to the CPU. And what the GPU is then designed for is this SIMD paradigm. So single instruction, multiple data. And that means that the GPU is set up to take one instruction, so for instance, one addition instruction, and perform that in a very wide manner. So instead of just adding 2 numbers, we add 32 numbers or much more than that. And we'll see that in more detail right away. I just wanted to mention that thinking about GPUs in the SIMD fashion is very important when programming, but if you go further into GPUs, you will actually see that it's not SIMD at the medium level. You'll find it's a single program, multiple threads architecture. So multiple threads can sort of run on the GPU simultaneously. So what we're actually looking at here is what NVIDIA calls an SM, a streaming multiprocessor. And the A100 GPU has 108 of these streaming multiprocessors, and these SMs then contain our smaller cores. So as you can see in the picture, this SM has a cluster of 4 of these smaller compute units, each with a load of small cores in them. So these smaller squares that says int32, FP32, FP64, those are CUDA cores in NVIDIA parlance. And these smaller squares are what is actually performing our computation. But we have to think about SMs, as we'll come back to a little bit later. But here you can see these SMs have they have caches, both for instructions and data. They have warp schedules, which we'll come back to, dispatch units, and tensor cores, which are a special new kind of cores that, in a sense, have just been introduced to GPUs, which are optimized for doing machine learning loads, so doing large matrix multiplication operations. And what's special about all of these small cores is that they're actually quite independent in some sense. As we've written here, the int32 and FP32 cores can actually run independent, which means that you can actually have 32 threads running on just one of these 4 clusters simultaneously. So how do we think about the GPU when we should program it? Well, I've tried to here illustrate how I normally think about the execution on a CPU. So what I've tried to illustrate here is 2 cores on a CPU, and these arrows represent a thread on these CPUs. And let's forget a little bit about virtual cores now. Just think of these as full cores, each having 1 thread running on them. So each of these threads have access to all of the compute units of this core. They can load memory, they can perform additions, multiplications, all of that sort of stuff without interfering with each other. So these threads are, unless they explicitly cooperate, they are 100% parallel. So both of these can do work at the same time. In contrast, on the GPU, these cores, these 4 compute clusters that we saw making up 1 streaming multiprocessor, actually don't run the threads individually. They actually run a set number of threads in a SIMD fashion. So each of the threads perform the same operation, but then work on multiple data. And that actually has a lot, that actually influences how we should program and how we should think about GPUs. Because on the CPU, we can think just, we have 1 thread of execution that affects everything. We don't need to think about what happens if this thread needs memory. all of that's just taken care of for us. But on the GPU, if we give this core too little work, we're just wasting compute, because the GPU will always run a set number of threads, even though we maybe only have work for, let's say, half of the threads, or just if in worst case we just have work for one thread, we're wasting all of the other threads that still have to run on the GPU, but they're now doing nothing. So that sort of influences how we should think about programming the GPU. And just to make it very concrete, in NVIDIA parlance, we always run 32 threads. For AMD hardware, it's 64. And then I've added an asterisk here because on Intel's new GPUs, they actually have support for different thread sizes. But as you can see, all of these GPU vendors have a set number of threads that they have to run anyway. So again, if you only have work for one thread, then you're wasting either 31, 63, or in the best case, 7 of the threads. And the lockstep execution we just talked about, but what that actually means is that for NVIDIA, for instance, these 32 threads actually run the exact same operation at each tick of the GPU, but access different memory areas. So if you, for instance, add an if and check, oh, if we're thread 0, then we should do some computation, and if not, then all of the other threads will still run a computing operation, but it will be a no-op in this case. But again, all of these threads must run an operation at the same time, only accessing different memories. And this has a lot of implications in how we can synchronize across the GPU. And we'll come a little bit back to synchronization when we talk about the memory subsystem of the GPU. But for now, it's probably enough to say that there is very limited synchronization between these thread groups. So within a thread group, we can actually synchronize quite a bit and do quite a lot. But that's only within 32 threads. And as I mentioned previously, the A100 GPUs have 7,000 cores that it can run threads on. So only synchronizing between 32 is actually quite limiting in this regard. And even within a streaming multiprocessor, we can synchronize quite a bit. But between streaming multiprocessors, and again, we have 108 of those, it's really difficult and starts to get really slow to synchronize. So compared to the CPU, where threads can synchronize, share memory, and do all of that quite quickly, that's something we can't do on the GPU. So again, to try to give you a little bit more of an intuition about how these threads work, I thought, why don't we look at how to visualize this? So on the left-hand side here, we can see a very small C code. We just define some data, and we just want to do, we just want to initialize it actually. But you can imagine that the loop could also do some computation or other stuff with this. So on the right-hand side, I've tried to illustrate how this looks in memory. And as you can remember from Marcin's presentation a couple of days ago, this is heavily modified truth, but it still helps us visualize how this works. So in the first iteration, we start at element 0. So the arrow points at the element that we're computing on. And then once the loop advances, the arrow advances, and we sort of eat this array one element at a time. But how should we think about this on the GPU? Because we can't think about just one thread of execution, as I've alluded to. So instead, we actually have to think about a group of threads processing this array on the same time. And I've modified this loop now to run with OpenACC, which is a directive-based technology that we'll get back to a little bit later. But the important thing here is to see that instead of having just one thread of execution that processes our array, we need to think about a group of threads. And with the difference in hardware, the thread groups can be different, as we saw, but it's always a group of threads. So once the GPU has processed one slice of our array, this thread group just moves on to the next one. And this is a good way, I think, to visualize how the GPU works. And another caveat with this is with the amount of cores that we actually have on the GPU, we need to be aware that the GPU can actually decide to run these thread groups in parallel. It can decide to give the streaming multiprocessor an order to run 2 for a lot of thread groups, and these can be scheduled at different times simultaneously, and there is nothing that tells us that thread group 1 has to run before thread group 2 here, and so on and so forth. So that's another difficulty in working with the GPU. So the last part of this is the memory subsystem. And I've tried here to illustrate the full memory subsystem with a bit of detail omitted. So on the left, you can see system memory, and that is the RAM that the CPU works with. And we have the GPU connected by some sort of bus, usually in an HPC context. This is the PCI Express bus. And the system memory then transfers to the GPU into what we usually refer to as device memory. But then, just as with the CPU, we have layers of cache, but it's very important here to note that the cache is not used for latency hiding. So what this means is that in a CPU context, for instance, when you read memory, Ole Vidar sort of explained how the CPU pulls in much more memory than what it actually needs. At the very minimum, it pulls in a cache line, but it can actually pull in multiple cache lines in different levels of cache, so on and so forth. But that doesn't happen with the GPU. Because the GPU is set up to run so many threads at the same time, it actually doesn't have enough cache and device memory to use that for latency hiding. So what we do instead in the GPU context is that we use the threads for latency hiding. So on the CPU, we fetched a cache row to assume that the next time we operate on memory, we'll read something close by. But the GPU, in contrast, it just says, oh, this single thread within a warp, so 1 out of 32 threads, doesn't have the memory in its register file. Well, no problem. We'll just suspend this whole thread group. So stop all of the threads computing, then wait for the memory before starting up again. And then to hide latency, the streaming multiprocessors will just schedule another set of thread groups. So if we don't have enough thread groups, then our computation will again be slower because we will just be waiting for this slower memory. But luckily, the device memory to cache is very large. So the transfer from system memory to device memory is around 6.5 gigabyte per second. But from device to L2 cache on the A100, it's actually 1,555 gigabytes per second. So an order of magnitude larger, which is how the A100 is able to sort of feed all of these thread groups. So we can launch multiple thousands of threads, and thanks to this wide memory bus, we can give all of them memory at the same time. Yes, so here I've actually added the numbers, so not 6.5 gigabytes per second, but 31 actually. But still a huge difference between GPU and CPU and memory, and how this all comes together. So just to summarize a little bit, when thinking about programming on a GPU, we need to think about single program, multiple threads, or ideally need to think in SIMD fashion. So single instruction, multiple data. So we're not processing an element and an element, we're actually processing a slice of data at a time. The GPU has a very high bandwidth internally and can have quite a lot of device memories. For instance, A100s on Betsy have 40 gigabytes of device memory, which in GPU terms is very much, but compared to RAM, maybe not that much. But this has implications for how we treat data on the GPU. So we need to try to keep the data on the GPU at all times, because transferring to and from system memory is slow. And we also need to think about how these threads actually interact with memory and how they use memory. Because if we use memory unwise within the threads, then the whole operation slows down. And as we discussed, we slow down quite a lot of the compute because we run in lockstep. However, the GPU is massively parallel, and that gives us a lot of benefits to work wide and actually tend to change the adage that we should save on processing. So in a CPU context, we usually add ifs and try to avoid processing array elements if we know that it's not used. So for instance, if you have quite large matrices and a lot of the elements are 0, for instance, in a CPU context, we could think about actually checking, oh, is this element 0? Then we don't need to multiply because we know the answer will be 0. But in a GPU context, it's usually a lot better to just let the threads do the computation and, in a sense, throw away threads, because these threads can help us high latency and actually get our processing done faster than if we skip doing computations. So that's how a GPU is working. So let's change gear a little bit and talk about the different GPU technologies that you might encounter when you're using GPUs, or if you're not even intending to program on a GPU, but maybe the software you're using is using GPUs. It can be nice to know sort of the underlying technologies. And I've chosen these 6 technologies to highlight, and I'll try to divide them into groups in the following slides so that you can see how these technologies differ. And we'll even look at a couple of code examples to see how you can actually use them in your own systems. So we have NVIDIA CUDA, AMD HIP, OpenMP is hopefully known to a lot of you, but lately OpenMP has gotten the ability to do GPU offloading, which is nice. OpenACC is probably another technology that a lot of people have heard about. It's very similar to OpenMP, but much more focused on accelerators and then GPUs in particular. Cocos and Raja are C++ libraries that can offload our computation. That we'll not see a lot of them in here, but it's good to know that they exist and that you can use libraries instead of needing a compiler or stuff like that. And the last technology that I wanted to mention is SYCL, And that's because it's really coming along and seemingly taking over a lot of the software within GPUs, and we're seeing quite a lot of heavily optimized programs actually transitioning to SQL to offload to GPUs, and so it's an important one to know about. So let's try to divide these into what sort of technology would you program these with? And of course, you could interface all of this from different paradigms. So CUDA, for instance, you can program that in some sense from Python, but the main technologies that these software stacks work with are C and C++, or C, C++, and Fortran. And as you can see, most of these are C and C++, while OpenMP and OpenACC are, of course, Fortran supported. And I've added an asterisk next to CUDA because Fortran CUDA actually exists, and you can write CUDA kernels in Fortran, but you'll not find a lot of examples of that. And there is very little documentation out there to help you get started. So in some sense, NVIDIA is heavily focusing on C and C++. So that's why the asterisk is there. We can further subdivide these software technologies into what sort of stack they are built on. And I've chosen to divide these into 3 categories. We have compiler-based, so that are the stacks that need their own compiler to work. Directive-based, these also need a special compiler to actually offload to the GPUs. But what I mean by directive-based is that you can add these directives into your code, and if your compiler doesn't support those directives, it will simply ignore them, and your code will still compile and everything. So with the right compiler, it will actually offload to the GPU, but with a different compiler, it won't offload, but it will still work. And the third one is library-based. And what that means is that you don't need a special compiler, but you do program in a different way to, say, the directive-based approach. You actually have to adapt your code to use the library. And it's a bit difficult to see on this slide, but I've tried to mark SQL as both library and compiler-based. And that's mostly because SQL actually hooks into these other libraries, these other technologies, to perform the offloading. So in some sense, it's library-based. But SQL is also a standard that needs a separate compiler. So SQL support is unlikely to be built in to the default compilers. So GCC, Clang, G-Fortran, and so forth. But the development isn't as heavy as with NVIDIA CUDA and AMD HIP, for instance, for the vendors. So supporting SQL from a vendor viewpoint is simpler than supporting NVIDIA and CUDA. Another way to look at these technologies is to think about them in vendor neutrality sort of way. So I've already mentioned that HIP and CUDA are vendor specific, again with a few asterisks that we'll come back to. And these other approaches are actually vendor neutral. So OpenMP, as you probably know, that's supported by a lot of compilers. So most modern C and Fortran compilers support OpenMP for CPU parallelism. And some of these are actually coming quite nicely along, adding GPU offloading. But the important thing here is that if you are using one vendor's compiler on one system, you can still take your code to a different system and compile it, and it should be able to run. Maybe not as optimized, but still it should work quite nicely. And it's the same with SYCL. That's a standard developed by Kronos, and so there is no single vendor there that decides how this should go. There are, of course, vendor-made compilers, but if you then develop your code in a SYCL-specific manner, you're not locking yourself into a specific compiler. So any conformant SYCL compiler should then be able to compile your code, even though you might prefer using your vendor's SYCL compiler rather than any other. And before we move on, I wanted to highlight these two asterisks because AMD would probably be a bit annoyed at me for saying that HIP is vendor specific, because HIP can actually support both AMD and NVIDIA hardware. However, I've chosen to call it vendor specific because it's not likely going to support other GPUs, so Intel GPUs, for instance. And it's very specific to the way these GPUs work. So if you choose to program in HIP, maybe you want the most performance possible, then it will be difficult to transition to other hardware apart from NVIDIA and AMD. And OpenACC is vendor neutral in that it's an open specification that anyone can implement, but it's a specification driven mostly by NVIDIA. And so you'll find the best support in the NVIDIA compilers, but GCC, for instance, also has support for OpenACC, and other vendors are on and off working on OpenACC support. So it's not a bad choice, even though it's the best choice for NVIDIA hardware. And then lastly, I wanted to talk a little bit about complexity and performance. And think about this as a graph going up or down, where OpenMP and OpenACC are the least complex technologies. So they're both the easiest to integrate within your own code, and also the simplest to think about. But it's more difficult to get the highest level of performance, but can be a difficult trade-off. So both SYCL and Cocos Raja are able to get most of the performance out of GPUs, and a lot more than OpenMP and OpenACC offloading. But if you really need the full device performance, you actually have to go all the way to CUDA and HIP to get all the specific knobs and whistles to really wring out all of the performance of these GPUs. So that can be a trade-off. But let's try to summarize this software technologies and what you should choose. So what I say to everyone is that your preference should be based on what hardware you have available. It's no use selecting something vendor neutral if your vendor doesn't support that, for instance. So hardware is what you should choose based on. Then comes the other sort of more difficult and not concrete choices that you have to make. So I would suggest always choosing vendor neutral software, because then you're not locked into one vendor. You need to think about your own code base. So who will develop the code? And you need to think about that it might take time to get everyone on your team to transition to the new library or this new software stack. And it can also be more difficult to onboard. For instance, most scientific compute students probably learn about OpenMP at some point. So introducing OpenMP for parallelism probably isn't difficult for a lot of code bases. But using, for instance, Intel's thread building blocks can be a bit of a hurdle and gives a bit of a learning curve. So you need to think about your own team as well when choosing these technologies. And the last point here is the most important, even more important than available hardware, always use an optimized library if you can. If you can avoid implementing something and you can use a library from one of the vendors, then that saves you a huge amount of time in implementation and in support of that stuff. And in addition, if these libraries are open source, you can also contribute changes back and then help others. With all of that said, I would probably, if starting a new code base today, either choose OpenMP offloading if your code base can support that and your developers are comfortable with OpenMP. It's a quite an easy choice that can get you quite a lot of performance. And if you're really confident in your team, then SQL is the best way to go because of its vendor neutrality and ability to give you all of the performance. It's really one of the best choices. Ideally, I would like to show you some code, but I see I'm running out of time for this session. So I know Stig will present these later as well. So I think we'll skip this and then Stig can talk a little bit about the differences as well as how you compile them. And we want to show you a little bit about OpenMP, CUDA, and SQL and how these sort of differ. So let's try to round off this introduction to GPUs with some suggestions of when you should transition to GPUs, what you should look for, and how you can get help. So again, I can't stress this enough. If you find a library that can do what you want, for instance, if your code base is heavily using BLAS, for instance, excellent. Then you can probably test out how that works on GPUs, either by using NVIDIA's dedicated libraries, AMD have dedicated BLAS libraries, Intel, so on and so forth. That's the ideal thing. And if you're using some larger software to do analysis, maybe you've heard about GROMACS or Gaussian, check with your vendor if they support GPU offloading, because quite a lot of larger software these days support some sort of GPU offloading. And maybe we here at NRIS haven't documented all of that, and just come to us with these sort of suggestions and we'll help you install GPU optimized versions of the softwares that you want to use. If you're developing your own software, there are a couple of things to think about to see if your software can fit on GPU. And if you have a large amount of independent data, then that's a good sign that you can transition to GPUs. Maybe you're doing a lot of very, very similar computations. So if you're doing large stencil operations, you're subdividing your problem area into small fine grids and then doing very similar computation on each of the grid squares. That's a good indication that you can accelerate on GPUs. And then the last part here is your team should actually think about if they want to support a GPU port or not, because there is a lot of help that you can get in porting your application to GPU. We here at NRIS, for instance, are available to help you port your application to GPU. However, you need to ensure that your team is actually willing to support, because what we experience quite often is that someone approached us to help them accelerate their software on GPUs. This GPU port then takes quite a lot of know-how and care to actually use. And the developers then tend to not want to keep that port alive. They don't update it. They implement new features that aren't GPU aware, and so this port tends to wither away, and that usually ends up meaning that you don't get the benefit of GPU, and the effort that we all put into porting your application isn't utilized as well as it could be. And that's it from me for this session. So the next session will go into more practical how you use GPUs at NRIS, and I'll just do boring slideshow presentations of that, but then luckily Stig Rune will do a bit more hands-on later, so you can see that. So if anyone have any questions, we can take that now.
Yeah, please. Sabri, do you have any question?
Thank you very much, Jørgen, to sharing your wisdom with us. So one thing I would like to ask is about, it's two things you may disconnect, you may answer them separately. So when you have like a single operation operating on like the multiple data sets, you need to get this data into the GPU. So can you comment on the bottlenecks? How would you get your data from the hard drive to this place where the actual processing happened? Does the data need to go through system memory, for example, where this path? And if I want to consider GPU processing, does the size of my data matter? Like, is GPU processing on smaller bits of data, or can larger bits of data also could be considered?
Yep, those are excellent questions, Sabri. So for the first part of that, yes, you will have to load in data from disk into system memory, then transfer it to device memory. Of course, that's a truth with some caveats. We're seeing technology emerging where you can just stream directly from disk to device, but let's try to keep it simpler. It sort of depends on the software technology that you're using, how this is done. But the rule of thumb here is to try to load as much of your data into the GPU as early as possible and just leave it there. If you transfer back and forth, you're losing quite a lot because the transfer from GPU back into system memory takes quite a long time. And so it very often happens to just be quicker to do the computation on the CPU and then avoid doing the computation on GPU and then transferring back and forth. So that's one of the first things actually that we look at when we transition software from CPU only to CPU and GPU. Is there enough computation here that the overhead of transferring back and forth doesn't take longer than just performing the computation on CPU? Then for your second question, depending on size, that's again a very good question, but also a bit difficult to answer in the general case. If you have very little data, you need to make sure that you're doing a lot of operations on it, because transferring a small amount or a large amount of data from system memory to device, it takes about the same time. It's the same latency to do that. So if you have a very small amount of data, you transfer it and you don't do a lot of computation on it, then you're probably better off just doing the computation on CPU. And that's why we usually say that GPUs are good if you have a lot of data, because then you can hide the latency of transferring to device by transferring a part of the data, doing computation on that, while you're transferring the next part of the data. So interleaving transferring of data with computation. I hope that answered your questions.
Thank you, Jørgen. Yes.
Okay. Thank you, Jørgen.